Today I'm going to talk about the first confirmed intermediate mass black hole tidal disruption event. It's like found last year, so it's a really new IMBH-TDE, and not a new, but it's actually the first confirmed one. Yeah. And quick self-introduction. My name is Wenkai, and I'm an undergrad, fourth-year undergrad from China, and I have been here for 3 months working with Anne. I'll stay here to probably the end of March next year. And in China, I do TDE, IMBH, and here I work with Anne working on post-Albers galaxy, which is a kind of really interesting galaxy because people found that tidal disruption event, which is a black hole disrupted stars, prefer to happen in this kind of galaxy. So, but like supermassive black hole and stars around it is like very center region of the galaxy, and the structure of the galaxy is very relative large structure. So it's fun to like probe the connection between galaxy scale to the black hole region. And that's what I'm doing here. But today I'm not going to talk about this. I'm going to talk about the connection between, or the combination of TDs and IMBH. And give some, I put some beautiful pictures here. That's actually how I started my astro journey when I was 12. And I asked my parents to buy like a 6-inch Newton telescope, and at the balcony of my house I took those beautiful images. It's actually not so easy, like not you use your phone and just get the image. Yeah, so actually I started to learn how to process those data like lucky image or something like that using those techniques. And this is when I was in back in China. I was the president of our Amateur Astronomy Association, so we organized a lot of exciting astronomy events. This is for, like last year, there's a very bright comet, so we go there and try to catch that. And this is last year, I was invited to give a lecture for the, like every year there's an International Astronomy Olympics, or called IAO or IOA, something like that. And this is Team China, so I give some lecture for them to help them prepare for their Astro Olympics. And I have a lot of hobbies like star party, travel, and data photography. And I used to love all kinds of sports, but I got a serious knee injury like 3 years ago. Yeah, that's sad. So I try to find some sports used only upper body, like arm wrestling or cue sport. Yeah. So that's when I was 14. Yeah. Those photos was in the photography of the year for astronomy. Not actually win the gold medal, but a short list. And I think I want to start with something related to transient, but not like directly related to today's topic, but it should be fun. We start as a guessing game. Somebody can guess what is this? This is like a week ago I took with my phone. Maybe get a closer look. Have any idea?
I was going to say Venus at first, but now it looks elongated.
Is it a comet, and this is just like it's very dark out and you have long exposure, so it looked like it?
Yeah. Really good guess. Ooh.
I took a picture of the comet the other week, and it came out exactly like this.
Yeah. Yeah. As an astronomer, we know how to do with the data, so we make it black and white and reverse the color. Now you see that. Yeah, and there's something like a tail. So I asked one of my friends, he did really good photography, so it's like this.
No, that's
So this is a transient that you can see with your naked eyes, and you might use a binocular at school. And it's actually called lemon.
Yeah.
So
That's the one.
yeah, that's the one. And why is it transient? Because it's non-periodic, so you only have one chance to see. And
I was out looking for it the other night, and I couldn't find it. But like I brought binoculars down, and then this bright fireball went across the sky. And I'm like, well, that was worth it.
Yeah. And just last week I was told by Kay that I don't find that lemon is just like Mount Lemon, like 100 kilometers away from here.
Yes.
Yeah, and it was found by this Catalina, one of the telescope of that. So super cool. And if anyone wants to see that with your eyes, I just know that like there's an Astro Cup here, and every Thursday evening they will do the observe evening. Like I think it's 6 p.m. to 8 p.m. Near the main library. So last week I go there and actually I saw that comet with those telescope, which is super cool. So I suggest everyone or anyone who is interested in that might go to, like tomorrow. Yeah. And let's go back to today's topic. First I'll go for a brief introduction about TDE and IMBH to make sure everybody has some feeling about that. And then we connect the combination of those. And for the first confirmed IMBH-TDE. And finally, I will talk about my model, which is like the light curve look really weird. It's not a typical TDE light curve, and we make a model to simultaneously explain the X-ray and optical light curve. So first, what is TDE? It's a star disrupted by a black hole. Here's an animations for you to see that. It's actually a real simulation by Steinberg and Nixon. This is in the star's coordinates. So at first, the star is actually approaching the black hole. So in the star's coordinate, it becomes stretched longer and longer. And the white arrow is pointing to the black hole. You cannot see the black hole, but it's there. And the streams go to the pericenter, and black hole is here. And actually, it will create some strong shock with itself and finally form an accretion disk. Why it will create a strong interaction called like a self-interaction is because the GR effect is so strong here. So the orbit will like precess due to the GR effect. And that's an important point. We will see that later. So classic TDE model actually actually already have some good result. A review article by Martin Rees is like already 30 years ago. Like people can predict the event rate by so-called loss cone theory. Is that like the stars is actually, there are many stars around the black hole, and it's like an unbody interaction or so-called unbody relaxation, and the stars will be scattered towards the black hole. And you can calculate the rate or something theoretically by that. And if a star's the pericenter radius is inside the tidal radius or smaller than that, it will be disrupted. And you can imagine that the stars is fly from very far away. So like the orbital energy of the star is approximate 0. So after this disruption, the energy like, how to say, some mass gets a positive energy and flies away, and like half of the mass is like get a negative energy and will finally fall back. And classic theory actually, I forgot to mention that the most bound debris, which is this one, and the time for it to fall back is called fallback time scale. It's usually like 10 days or 20, 30 days, something like that. So classic theory actually thinks that when the mass fall back, it will immediately create an accretion disk and immediately be accreted. So they ignore the time required to form an accretion disk and ignore the time to be accreted. And for this simplify, you can get a very cool analytical result that luminosity is proportional to a polar decline. And we'll see that this simplify might not be true, especially for IMBH-TDE. And you can calculate the spectrum or STED by modeling as a disk, but like a multi-color or multi-temperature back-body disk. And you can predict that it peak at UV or soft X-ray. So this is the classic model and fast rise and polar decline. Actually, some of the first discovered X-ray TDE is just look like this, fast rise and polar decline. But we should be very careful because they actually select those samples using this criteria. So of course they only select those kind of TDE. And as we found more and more TDE, this is 9 TDEs, and here is the optical and UV light curve, here is the X-ray light curve. You can see that the light curve looks like not a simple fast rise and power law decline, especially for X-ray. Like all of them looks different. So the simplified model is good, but for TDE we might need a more detailed model about the light curve. Okay, so ABC for IMBHs. Why we care about that? Because it's connect between stellar mass and supermassive black hole. So people think that every galaxy, most galaxy, large galaxy, there's a supermassive black hole at the center, and people think that they grew from IMBH, which is intermediate mass black hole. So this is a very important kind of black hole to probe the growth history of supermassive black hole and also connect those two kind of black hole. So we need to find more, and the confirmed IMBH to date is like less than 10 or approximately 10. So just very few one. So it's important to find more so we can get a better study on that. So a better way, or not a better way, I mean a good way to find IMBH is through TDE, because especially for those inactive IMBH, if the IMBH is not active, meaning that it's not on a accreting process, you cannot see them. Especially for those far away, you cannot use dynamic ways or other ways. But after TDE, there's a stellar debris and can trigger accretion process and something like that. You can see the black hole and can find the black hole. So that's really interesting. The question is, have people found IMBH-TDE? I just say that we have found, but yeah. The first candidate is also very near. It's like, it's just 8 years ago by Da Chenglin. It's here. This is a large galaxy and it's on the outskirts of this large galaxy. But they found from an archive data of XM and Newton, so they only have a decline stage light curve shown here. And they do not have an optical light curve. They do not have an optical spectrum to confirm that it's a TDE. So this is just a candidate. But people who do theory already do something to support that this kind of X-ray light curve for IMBH-TDE can be the case. They actually use a very simple model which is commonly used in TDE for the accreting process. It's not even a 1D accretion. This model is like a 0 dimension. Yeah. So everyone can understand this. The mass of the disk will change. Why? Because there's mass goes into the disk, which is the fallback rate, and there's mass be accreted, which can be calculated by the disk divided by the accretion time scale, or so-called viscosity time scale. And this is actually, you can integrate that or use numerical method to solve that. So but a big problem is they ignore the time to form an accretion disk. They just simply think all the mass that goes up and fall back will directly goes into the disk. But that might not be the case. You can imagine that you just put a mass there and it can orbiting around the black hole again and again. It's not necessary to be accreted unless it become a circularized orbit instead of after the disruption is a very elliptical orbit. So that's the key point for their model that they do not consider. And their model will predict a fast rise because they do not consider the time to form an accretion disk. And then a flat light curve, which called a plateau or something like that. This is because usually we think that the luminosity will be proportional to the accretion rate. But if the accretion rate is super ident, usually by advection and outflow or something like that, the luminosity can't go up a lot if it's super ident. So if you see a flat plateau in TDE, it probably means it's super ident process in this way. And finally, a decline stage, which is proportional to the fallback rate. You can simply calculate that, like, let the t to infinite, and you'll find that accretion rates will follow the fallback rate in their model. So their model apply for this candidate and see that the late time light curve fits quite well, meaning that supports the IMBH-TDE scenario, but the thing is they do not have spectral confirmation for this candidate. So it's still a candidate. Okay. So time goes to last year. This is China X-ray time domain telescope. It's super cool because you can see the field of view, super large. It's like it can scan through the eyes half of the sky in 5 hours. So you can get a very high cadence X-ray light curve. And there's also a follow-up telescope, like the 212 telescope here. It's like just like the Eero-Theta telescope, but Eero-Theta have 7 and we have 2 for the follow-ups. So after it was launched in February last year, and during the you can see here it's like March or April last year, we confirmed IMBH-TDE. So this telescope is really efficient to find IMBH-TDE. I will talk a little bit about that, why it's very efficient. And why we confirm that, because we have spectrum and it is real-time captured. And also we have multi-wavelength observed, which is weird. That is what my model will solve this problem later. And why is this an IMBH-TDE? Oh, I forgot to mention that this is the large galaxy, and this is where we found the TDE. So it's not in the center of a large galaxy, but the redshift is the same. So meaning that the host of this TDE is a globular cluster or a dwarf galaxy around that large galaxy. And so that's super cool. And why is the TDE? First, spectrum. It shows typical H alpha, H beta, and like helium-2 and the boron nitrogen line or something like that. It do not support AGN because we do not see any oxygen 3 we typically see in AGN. But their left problem is that usually the line of TDE is super broad. It's like 10 to the 4 kilometers per second. And for AGN, it's like 10 to the 3 or something like that. So for this one, you see that the line width is like 10 to the 3 or 2000 or something like that, which is not consistent with previous discovered supermassive black hole TDE. But since we do not know a lot about IMBH-TDE, maybe the mechanics to draw the line for IMBH-TDE and supermassive black hole TDE is different. People believe that for supermassive black hole TDE, the kinematics is not enough to draw that 10 to the 4 kilometers per second line. So suggesting that it can be because of electron scattering, like because TDE is a highly ionized, like near the black hole, so a lot of electron, and through the scattering it can broaden the line. But for IMBH-TDE, it might be different. And if the line width for IMBH-TDE is mostly account for the motion of the debris or the accretion disk or something like that, it can be like a 10 to the 3 kilometers width per second width. So this is an unsolved problem because we really, like, both by theory and by observe, we really just know little about the lines, emission lines about IMBH-TDE. So this is not like, still is a mystery, okay. But we also have a lot of other things to support IMBH-TDE, which is first, why is an IMBH? Through the host luminosity, you can estimate the black hole mass, and through the X-ray SED fitting. Usually, like a smaller black hole or lower mass black hole will have a higher temperature accretion disk, the inner region of the accretion disk. And this is like 200 eV, which is typical TDE is like 10 to 100 or even less. And typical AGN will have a power law component, which is from the corona. So its SED was, I think I show here, is just as the theoretical prediction for IMBH-TDE. So that's a support. And another support is, of course, for that it looks just similar to that candidate. It's on the outskirts of a large galaxy and something like that. And the last one I will show later in my model with more detail. That our model also fully support that. And in the discovery paper, actually people using much more things to, I think it's like 6 or 7 methods to say that it's actually an IMBH, and they all consistent with a 10 to the 4 to 10 to the 6 mass solar mass black hole. Yeah. So finally to my model. You can see that the light curve look very strange. We just say that classic model predict that TDEs fast rise and power law decline. But the X-ray light curve rose remarkably slow on the timescale of 2 years. Although no observer here, it's become 100 times brighter in 1 year. The x-axis is linear but not same scale, so look a little bit weird. Like this is 2 years, and this is 1 year. Okay, and then a plateau and then a decline. And the optical, we only have a upper limit for that, meaning it's very faint at early times. And then the optical light curve shows a plateau and decline, follow the X-ray light curve trend. So it's not a simple fast rise power law decline, which definitely needs a new model. And it's also not as the previous IMBH-TDE theory predict that it's a fast rise and a plateau and then a decline. So for that, we also need a new model. Our most important change for their model is that we put this fallback rate into so-called mass feeding rate or mass supply rate, meaning that the fallback material is not necessary to go into the disk, it can still orbiting. So we should calculate how much mass goes into the disk and why the mass will goes into the disk, because it can just orbiting around the black hole. Okay, so it goes to our model. This is the first step, which is the disruption, and it's a very classical treatment, because you can imagine that if you have the parameters for the black hole and the star's orbit, you should be able to calculate, or by simulations, what's happened after the disruptions, like all the parameters of the debris you should be able to calculate or by simulations. So there's already simulations for that, we just use that. And the initial stage, we record out in that animations, like the mass fallback, and it will turn an angle because of the GI effect and heat itself, cause some strong interaction here. This is very important. It will create, not creating X-ray, but creating UV and optical lights. We calculate that and shows that for IMBH, this is very faint. So this is good, consistent with the upper limit. And classic, not classic, but previously people have a model already for this. Like you can imagine that it have self-interaction, so assuming that angular momentum is conserved, but they lose energy. So they goes into another orbit, which is more circularized, but still very elliptical. This is called the second orbit, and then the third orbit, fourth orbit, after orbiting around the black hole. But in simulations, people find that there will be some inflows, which is super important. Just a very small fraction of inflow, but it will go to the black hole nearby region. So, and also it's seen in the simulations. So we propose that, for the slow rising stage of the X-ray, this is super important, the inflow, because it can go to the black hole nearby region, and for the nearby region, GI effect and something like that is much stronger, so it will interact violently, release energy, and produce a circularized accretion disk. You only need a very small mass disk because the luminosity is low. It's like 10 to the 40 at early stage, or 41, 10 to the 41 erg per second. But this is super important because it can explain the slow rise X-ray. And the next thing is, although no observed here, there's a fast rise. And this is the most exciting things about our model. It's like, how can you create a fast rise? Like it's just slow rise, and why is turning a point and becomes fast rise? And our idea is like this. at first the stream is contains most of the mass of the stars, the big disrupted stars, and the disk is very low mass. But as the disk mass grows, at one time its rotating momentum flux becomes comparable to that of the stream. The stream cannot go through the disk like we just show here. It can go through the disk and goes to the next orbit. But when the mass of the disk becomes larger, at a certain point, the stream cannot go through the disk. Instead, it will interact with the disk very violently in a very short time scale. So in a very short time scale, like 5 days or 10 days, all the mass of the stream is like half of the stellar mass. It goes into the disk. So the disk mass goes up like 100,000 times, and the accretion rate goes up like that. The luminosity won't go up like 100,000 times because of, which I said, advection and outflow, but it will become to the attenuated luminosity, which is here. So this is why it can becomes 100 times brighter. This is also already seen in the simulations, so super cool. And then for the plateau and decline stage, which is already well explained by previous model, so I will skip that. But I will point out that we see that there's optical comes from the plateau and decline stage. So where's the optical come from? It's because during the super-identity accretion rate stage, a lot of outflow will create. So those outflow can be as a reprocessing layer. It's like some X-ray photon will goes into the outflow and become reprocessed to the optical and UV photon. So that's also why the optical light curve will trace the X-ray light curve. And you can see that it's not easily seen, but there's a 30 days delay for the turning point of the X-ray and to that of the optical light curve, which is also consistent with this, because you can imagine that the photon needs to go to the reprocessing layer and then goes to our telescope. It's take a longer distance, so there's a delay. And the optical also just goes down like 2 times, but X-ray goes down an order of magnitude. That's also because of the reprocessing. You can imagine that the center source luminosity goes down quickly, and the outer region, because it reprocesses that, so it won't go down so quickly. And finally, I will say that why the outflow don't block the X-ray is because people already shows in simulations that this is called a unified model for TDE, is that it's not just for TDE but also for like ultra luminous X-ray source. Is for the polar region is optical thin, so you can see through that to see the inner disk, and this shows visible like an angle effect. If you see edge on, you can only see optical, but if you see face on, you can see X-ray and optical. Okay, so finally it's the decline stage. You can see that finally it becomes a power law decline. This is just as previous model that predicts, because it will finally trace the fallback rate, and that's also super cool. And so this is our fitting result. Our model fits the very weird light curve very well. And I block some data point here is because the at that point there's like some solar some flare from the sun which affect the X-ray data. So those are the good data point, and we fit it super well. And so that's a really interesting result that shows even the light curve look super weird, we can explain all of them. And also the upper limit of the optical light curve, the shade here is for uncertainty, is consistent with the optical upper limit. But there's optical plateau and decline stage. I don't do that because the discovery paper already do a Monte Carlo simulation for that. So combined with their result, we can simultaneously explain the X-ray light curve and the optical light curve at the same time, which is very weird. So some people think that this is not a TDE because the light curve is weird. We explain that this is a TDE and explain the light curve. So that's super cool, and this is for the summary. This EP source is the first confirmed one, IMBH-TDE, and we reveals that the circularization, which is to form an accretion disk, is super long for IMBH-TDE. So that's why it's a very long, slow rise. And we reveal the delay stream disk interaction, which caused that very weird turning point, and also reprocessing corresponding to the optical light curve. And actually, our fitting can give many parameter constraints, but the most important one is the stellar mass, and this is for describe whether the TDE is like a full TDE, meaning that it's totally disrupted, or a partial TDE. So this is a nearly full TDE, but with some uncertainty. But it's not a very extreme parameter, on the extreme parameter space. So this is very good, meaning that we don't need some very extreme parameters to explain the weird light curve. So that's all. And I have a final guessing game. Guess what? Today is my birthday.
Oh, happy birthday.
And this is a photo when I was a freshman, took with my parents. This is my university back in China. So that's all. And welcome to any question.
I had a question.
Mm-hmm.
Sorry. So you talked about simultaneous X-ray as well as optical observations,
Mm-hmm.
right? Where does UV come in the picture? Do you know? Like,
Yeah.
or
Actually,
is it
we
UV
only.
optical
Yeah. Actually, we only have optical light curve, but people think that, like here,
But do you? would
this
you-
one,
Yeah.
the self interaction, it will create UV optical, which is like peak between UV or optical. And actually, I calculate that this is actually will peak in optical, so UV is also expect to be faint. Yeah, and also there are other interaction, which is like some more like there are some mass that's continue fallback called tail stream, which is like the orbital energy is negative but very close to zero. So their fallback will also interact with those already orbiting around stream. That will also create a shock and also is a faint UV optical light curve. And the third one is a nozzle shock here, which is like when the stream become very close to the black hole, the gravity will like is how to say, it's like the gravity is very strong, so the stream becomes thicker and thinner, which is also a kind of shock. So this is also create UV and optical, and this is two things. It's like less than 10 to the 39 erg per second, so it's not a fact. So the most important one is this one, and is peak at optical, and that's how I calculate this early optical light curve for the upper limit. And the uncertainty is for I don't mention here, but like for the first few orbits, we show the thin stream here. Yeah, it's thin, and after a first few orbits, I make it like a very thick stream. That is because the optical depth of the stream is super high, so it will expand, and so this gives an uncertainty for the for here. This is because you don't know when it turns from an optical super optical thick to not super thick one, but probably the light curve will be like this. You can see my mouse, it will be like this. So at first it's super optical thick, so it's on the lower limit of this two light curve, and as it goes more optical thin. It's actually not optical thin, but relative thin, and it will like here. So the real light curve will be something like this, which is also consistent with that. But the model has some uncertainties, so you can change that. The most important one is like the efficiency for that self-interaction, because it might not be like 100% of their relative speed that all turns into the there's a relative speed of the two streams. It's not like 100% of their relative speed will turns into the thermal energy and all turns into the emissions. So there's some uncertainties on that. Yeah.
Do you have any constraints on the stellar population around this intermediate mass black hole? Like, would you expect 0.6 solar masses to be the general size of stars around this object?
Yes, actually, I think the Discover paper do a fitting for the host, and like 0.6 is a commonly seen one. And actually, usually people think that the most common TDE actually will be like 0.1 is the lowest mass. Mm-hmm. And as the mass goes up, the rate will go down, mostly because there are more low mass stars. Mm-hmm. So 0.6 is quite a good result. It do not require like a 3 or 5 or 10 solar mass like that. And especially if the host is a dwarf galaxy without recent star formation or a globular cluster, you don't expect a very high mass stars in that. Mm-hmm. Yeah. Oh, actually, there is something interesting. I talked with Kate and Colin and Noah. Is that let's see. Is that we don't detect radio for this one, which is weird, because I might have too much backup, but let's see if I had that. Oh no, I can't find that. Too much backup. Basically, people find, oh, here, yeah. A very fast outflow component in the X-ray, like assume this is an emission line, and it's very fast outflow. And I talked with them, they said probably this will create some detectable radio emission, but no. So it's a little bit weird. Yeah. And this is a very near IMBH-TDE, so it's not far away.
Maybe in later times we will wait.
Yeah. Yeah.
TDEs
definitely need to keep monitoring. Some TDE have like late time radio, like 1 year, 2 year, or even more. And suddenly there's a radio. So, yeah, really interesting.
Cool. Any more questions? I see we are already 10 minutes past. But if that's it.
I mean, I guess my question is, like, are there any variations in, like, does it matter how the original orbital plane of the star aligns with the spin? Because I noticed in...
Yeah, that's a super good question. I might not follow my... but I can explain. Yeah, actually, we have a free parameters for that. Okay. It's like, and a super cool thing is that, oh, actually I have it here. Yeah, it should be this one. Oop. Like at first the orbital plane of the star, or after the disruption is still the same orbital plane. Mm-hmm. It might not be the same as the black hole spin axis. Right. So it will make the accretion efficiency or something related to that be different. So we have free parameters in the fitting. We can also constrain that, but it won't make a very huge difference because if it's like the same rotation or not like another direction, it will only affect the accretion efficiency on the same order of magnitude. And so you can don't consider that, or we do it more precise. We have parameters that can be constrained using our fitting. And interesting thing is that there's a paper that says the accretion disk will align with the black hole spin very quick.
Yes.
Yeah, this is because the fallback mass is like continue, like the accretion disk will precess around the black hole due to GI effect, and the continual fallback mass will give some torque to that, and this will create very strong torque to make the disk align with the black hole. So that needs you need a lot of mass to go into the disk, because that can create a lot of torque to do that. So in our model, during the fast rising stage, this is the key point. At this time, a lot of mass goes in. So in our model, after this time, we use the same direction for the spin of the black hole and the accretion disk. So after this time, the accretion efficiency is determined, because we already know the black hole spin via the X-ray spectrum fitting.
Right.
That's doing the discovery paper. So after this point, we can have less free parameters, which is also how we done this. Yeah.
Okay, that's really cool. I guess what I was thinking was, I was wondering if the timescales at which the disk becomes like massive could be different. If I guess what I'm uncertain about is if when the disk is in its like state where it's very light, if the timescale for the disk aligning with the black hole is like short enough that even the rarefied disk aligns, or if this is only something that happens when the disk is really like massive.
Yeah, there are two ways for the disk to align with the black hole. One is through like this kind of fallback mass to give a strong torque, and another way is like I forgot the name, but it's like the torque in the disk itself will make it align with the black hole spin, but it will be very long. So yeah, we calculate that time. I forgot that, but it's definitely longer than several years for IMBH-TDE. Yeah.
So like I don't know what it is, like Bargeen-Peterson or something, or Lens-Thering or whatever timescale.
Yeah, yes, something like that.
The only thing that really matters is the torque of stuff falling into the black hole then, that like aligns what was the other process that aligned the...
Yeah, the only matter is when a lot of mass is going into the disk, and when it goes into the disk, the precise disk and the mass that goes in will create some very strong torque, will align even less than the fallback time scale. So it's like less than 10 days or less than 5 days, something like that.
Okay.
Yeah.
And I guess there's not like a way to get like streams then that like miss the disk or miss each other or something. You always get this stream collision.
No, it is possible. So we also account for that.
Okay, cool. Yeah, because that's what I was wondering. Is I was like, okay, everything's on the equatorial plane. Sure, the stream collides with itself. Then there's a disk. Eventually, the disk gets thick and everything. But I noticed the spin you mentioned in one of your models was like
the stream will definitely interact with the disk, but the stream may not interact with itself. Because of another precession if the black hole have a spin. Yeah. So we will also account for that. Yeah.
Cool. Thanks.
I think that's it.